So finally we've hit polynomials, but actually you've been here before. Because what polynomials are they're continuous. Okay, so if I draw a graph of a polynomial, it doesn't have a break. Okay, and the two polynomials that you've seen so far are linear and quad. Okay, so they're the two polynomial functions that we've looked at. So notice something about the linear function, like the most basic one is y equals x. It has a power 1. Okay, so we call that a polynomial of degree 1. We've used or seen quadratics, and that has the highest power in this polynomial is power 2. So this is a second degree polynomial. And in methods, what we're going to do is extend that out to look at power 3, power 4, power 5, etc., etc. Now note that these powers can only be integer values, and these powers are also always going to be larger than 0. Okay, and you might wonder why. Well, if I've got x to the negative 1, I've got 1 over x, which is a hyperbola. And notice how I couldn't draw that continuously. I had to lift or draw this part, lift my pen off and draw that part. So this is not continuous, therefore not a polynomial. But more on that later. Let's just review some function notation. F of 1, where this is the function, says basically slot 1 into the function and tell me what you get. So it's 4 times 1 is 4. 4 take 3 is 1. So f of 1 is simply 1. This one says, what value would I drop into the function to make it, to get negative 3 out of it? So that's just like saying negative 3 is equal to f of x and solve. Add 3 to both sides, divide by 4. It would be dropping 0 into the function. F of 3 is 4 3s are 12. 12 take 3 is 9. F of what gives me 17? So 17 equals 4x take 3. 20 equals 4x. X is 5. So it would be f of 5. F of negative 1 is negative 4 take 3, negative 7. F of what gives me negative 11? Negative 14 equals 4x. X is equal to negative 7 on 2. It's allowed to be a fraction. You're allowed to put fractions into functions. F of 0.5 or f of a half, that means a half of 4 is 2. 2 take 3, neg 1. F of what gives me negative 5? So negative 5 equals f of x. That is going to be negative 2 equals 4x. X is equal to negative a half. So if you chuck negative a half in there, you'll get negative 5. So there's just a quick recap of functions, or a way to dust off the cobwebs a bit. Okay, so let's have a look at this polynomial. It's a degree 3 polynomial. We'll get a name for that. It's called a cubic function. Okay, so, and that really is the focus of this chapter or this exercise. So we want to find p of negative 1. Now, interestingly, this Cambridge textbook seems to use, whenever they have a polynomial, they seem to use this capital P for the function name. Now, you're in no way, shape or form obligated to do that. And Cambridge, it just seems to be something that's unique to Cambridge. I don't see other textbooks do it, and I certainly don't see it on exams. But when they've got P of, that's they're indicating, or Cambridge is indicating that they're dealing with a polynomial. So P of negative 1 means chuck negative 1 into this function here. So negative 1 cubed is negative 1. Take away, we've got negative 1 squared, which is 1. 1 times negative 3 is negative 3. Take 2. And that's going to be negative 4, negative 6. P of 1, and negative 1 is negative 6. Okay, P of a half. We've got a half cubed. Take away a half squared times 3. Take away 2. 1/8. This one is going to be, what did I write? Power 2 there. Negative we're going to have 1 to the power of 2 as well. Oh, look, let's just do more working out. 1 over 4 times 3. I'm just trying to cut corners here. Every time I do that, I stuff it up. 1/8 take away 3 on 4 take 2. 1/8 take away 6/8 take away 16/8. That's going to be -5, -15, -21 on 8. So P of a half is -21 on 8. Okay, a little bit of function notation here. So we've got Q of x, some sort of polynomial. It's a degree 6 polynomial. That actually doesn't have a name. We just call it power 6 function. Is this where we've got an a value and a b value. So Q of -1 is the same as Q of 2. So this is saying if I drop -1 into Q, I get the same result as if I drop 2 into the function, and the result in both of these equations will be 0. Okay, so they're saying when x is -1, Q of x is going to be 0. And when x is 2, Q of x, or the function, is going to be equal to 0. So let's do it. 0 equals. Now I'm going to drop -1 in. So -1 to the power of 6 is simply 1. So that's going to be 2. -1 cubed is -1. Subtract -1 is +1. -1 squared is 1. So that's going to be plus a. And -1 times b is take b plus 20. All right, so notice as a result of this, I've got an a and a b as the only unknown. That's interesting. Now let's do it again for Q of 2. Okay, so I've got 0 equals, and now I'm going to put 2 in. So you need to know your base 2. So 2 to the 6 is 128. All right, I know that. And the way to work it out is to start with one that you kind of can remember. So 2 to the 4, most of you would know that that's 16. So 2 to the 5 is 32. So 2 to the 6 is 64. Good one, Mr. Miller. Lucky I checked that. There you go. 2 to the 6 is in fact 64. Now we're going to multiply that by 2, which happens to be 128. That's just a fluke. Take away 2 to the 3 is 8. Plus 4a plus 2b plus 20. Okay, what do we got here? 128, take away 8 is 120. 120 plus 20 is 140. 0 equals 140 plus 4a plus 2b. Right, so what we want to do is set this up for elimination. So I'm going to multiply this one all by 2. 0 equals 2a, take 2b plus 46. And I'm going to call this 1, I'm going to call this 2, and I'm going to do 1 take away 2. Why? I don't know. I feel like it. So this is going to be 140 take away 46, which is 94. 4a take away 2a. So it's good that I talk this through. So subtraction here, I'm trying to eliminate b, and subtraction is not going to eliminate it. Okay, so this should be 1 plus 2. All right, so forget 94. Let's add them together. So we're going to get 186. 4b take, so we've got 2a and 4a is 6a. 2b plus -2b is 0. -186 is 6a. Well, these numbers are a bit unruly. All right, 6 into 186. 6 goes into 18 3 times. 6 goes into itself once. So a is going to be -31. All right, now we're going to sub this into something. All right, so which one am I going to do? I'm going to put it into this one. 0 equals -31 take b plus 23. 0 equals, that's going to be 7, 8, -8 take b. 8 equals -b b equals -8. All right, that was a bit harder than I thought it would be. Okay, so this is a problem that really lends itself to CAS as well, and it's a common methods multiple choice problem. So here's how we're going to do it. We're going to define our function 6 take away x cubed plus a times x squared plus b times x plus 20. And then what I'm going to do is, where is it? Simultaneous equations template. I'm going to say f of -1 is equal to 0 and f of 2 is equal to 0. And I want to solve for a and b. And what I'm hoping here is that the answer says -8 and -31. Please, please, please. Yes. Okay, -31 and -8. So you can see there that the CAS will speed up the process and minimize some of the legwork there. I'm surprised I got that right. So there it is there on CAS. That's how you would do it on CAS. Hey, when you got functions, you can do all sorts of things, and we just make crazy functions next year by subtracting them, adding them, multiplying them, dividing them. We can do all sorts of things. So this one says, can you remove q of x from p of x? So yeah, we can. So we're going to say that p of x is this, x cubed takes 6x plus 3, and we're going to take away x squared, take 3x plus 1. Now, I hope all of you have all of a sudden shot up and looked at this video and thought, oh my God, what's he doing? He's subtracting that, but he's forgotten the brackets. Okay, so make sure you use brackets when you have to subtract multiple terms here. You've got to slot all of it because it's saying, I want to remove all of this, not just the first term. All right, so let's go ahead and do it. X cubed takes 6x plus 3, take away x squared plus 3x, take 1, clean it up, x cubed, take away x squared, take 3x, what do we got? Plus 3, take 1 is plus 2, right? So p of x, take q of x equals this, equals this, equals this. All right, this is a bit nastier. Oh, don't really want to do this. Okay, this is saying we're going to multiply these two functions together. So what we're going to do is say that this is equal to x cubed, take away 6x plus 3, x squared, take 3x plus 1. Oh, this is pretty nasty. Okay, I'm going to revert to CAS on this one and not do it by hand. If you want to try it out, you can. But what you're going to have to do is multiply that, and multiply that, then multiply that, multiply that, multiply that, then multiply that, then multiply that, then multiply that, and then you're going to have to clean it all up. So this video will end up being about 48 minutes long, and no one is going to watch that. So I'm going to go expand x cubed take 6x plus 3, and the other one is x squared take 3x plus 1. And that's what we would have got had we done that. So feel free to ride the roller coaster of this problem if you want and do it. It's good work, good sort of algebra work, but between you and me, that's not a lot of fun. Okay, so we've talked a little bit about the language of polynomials already. So it can be written in this form here. I think students find that really quite intimidating. But what I'm going to do is just go to a couple of rules. So the number 0 is called the zero polynomial. Now, why is that important? Might come back to that later. The leading term, ANXN of a polynomial, is the term of the highest index among those terms with non-zero coefficient. So what it's saying is the leading term is going to be of the highest power. So like x to the 5 is the highest power, or x to the 4 is the highest power, or whatever your polynomial is, That's called its leading term, the one with the highest power. In this case, power 5 polynomial. The degree of the polynomial is the index n of the leading term. So like I said, power 5 over here, power 3, which is also called a cubic function. A monic polynomial has a leading term with a coefficient of 1. That is monic, or mono, meaning 1. I don't know whether you do that, but when I was younger, I used to pull monos on my BMX and think I was pretty cool. Mono means you pull the front wheel up and scoot along on the back wheel. So that's what a mono is, and that's what I think about when I think about monic polynomials, is a young Mr. Miller shredding it on a BMX. Well, thinking I was anyway. The constant term is the term of index 0, so it has a power 0. This is the term index 0. It's not a power 0. This is the term not involving x. So our constant is 3, and our constant is 2 there. So state the degree coefficient of the leading term and the constant term for the following polynomials. Okay, so what we've got is a degree 3, or cubic. The coefficient of the leading term is 5, and the constant is 4. All right, let's have a look at this one. Oh, tricky. So the leading term, the degree of this, look at this, it's power 4. Okay, so it's a degree 4, and we call this cubic, we call this a quartic. So it's a quartic function, power 4s. Now, so the degree is power 4, or degree 4. Coefficient of the leading term is going to be the coefficient of the highest power term. So even though this is the last term, they're trying to be a little bit tricky. And actually the coefficient is the one of the highest power. So the coefficient of the leading term is a half in this case. And the constant term, it doesn't have one. So it has a constant of 0. All right, now this one here, it's a bit of a trick question. Okay, because see that? That's 7 over x to the 3, which is, you haven't seen that before, but that behaves very similar to a hyperbola. And because of that reason, hyperbolas can't be drawn in one continuous motion. I've got to do this part here, then grab my pen, lift it up, and bring it over to here. Remember, the idea of polynomials is they can be drawn with one consistent stroke of the pen. So this one here means that it's not a continuous function, so it is not a polynomial. That's important to know, because when you're thinking about what the graph might look like, it's important to know, what you're going to get, i.e. polynomials continuous, but ones with negative indices, not continuous. Okay, so on to probably one of my favorite techniques, and Mr. Tench talked about this for years to me, and I never liked it. And then one day I thought, oh my God, what have I been missing out all this time? And it's called equating coefficients, and it's one of the best techniques that I think is around to solve problems. And one 3-4 methods question every year involves using this kind of idea of equating coefficients. So here's a fairly easy one. So I've got, if ax squared plus bx plus c is the same as this, they want us to find what a, b, and c is. All right, so what I'm going to do this is leave the left-hand side as ax squared plus bx plus c, because there's not a lot I can do with that. And I'm going to start to manipulate this. I'm going to expand the perfect square, which is x squared, not take 9. It is take 6x plus 9 plus 5, which is the same as x squared take 6x plus 14. Now notice that these two things are the same. And that means that I've got a squared term and a squared term. an x term and an x term, and a constant term and a constant term. So all I can do is link up these a values with these coefficients, i.e. equate the coefficients. So a must be the coefficient of this. So a is equal to 1. B must be the coefficient of this. B must be -6. And C must be the coefficient of this one here. Oh, that's what that thing was talking about, power 0. Yeah, anyway, which is equal to 14. C is equal to 14. So that's how I would solve that via equating coefficients. Now, we put ones, put some simple as this on the Year 12 exam or the Year 11, Year 12 SAC or Year 11 test. And you guys invent all sorts of weird and wonderful ways to try and solve this, but really it's just pair up the coefficients, let them equal each other. All right, this says here that this polynomial can be written like this, where B, C, and R are real numbers. And what they want us to do is find those values. So for this one here, we're going to say that x cubed plus 3x squared plus 2x plus 1 is equal to, or can be written as, x take 2, x squared plus bx plus c plus r. So what we're going to do with this is I'm going to expand this out. So that's going to be x cubed plus bx squared take, no, hang on, what am I doing? Plus x or cx take 2x squared take 2bx take 2c plus r. Okay, now let's put this together a bit better. Now, can I pair something up? I can sort of. Okay, I'm going to write this as x to the 3 plus bx squared take 2x squared plus cx take away 2bx take away 2c plus r. Okay, so now what I've got to do is get it down to one lot of x squared. So to do that, I'm going to say x to the 3 plus x squared b take 2 plus x c take 2b take 2c plus r. Okay, now I'm ready to pair up some coefficients. So this could also be written as x cubed plus b take 2 x squared plus c take 2b x take 2c plus r. So that equates to that. So b take 2 is equal to 3. B must be 5. There you go, we've got our first value. This is c take 2b must be equal to this coefficient, 2. And that's convenient. We just found out what b was. So c take 2 times 5 equals 2. C take 10 equals 2. C must be 12. All right, and now we've got -2c plus r equates to the constant term. So that, even though it looks like two terms, is just a constant because these c and r and b values are just parameters. So we've got -2 times 12 plus r equals 1, -24 plus r equals 1, r equals 25. All right, so there's our b, c, and r values. Okay, so equating coefficients. I mean, that might look tough to you, but think of another way to do that problem. I don't know it. Okay, so now it comes to the point where we've got to try and expand polynomials of this form here. Now, we've seen a plus b to the power of 2. That's the perfect square expansion. What about for a power 3? What about for a power 4? What about for a power 10? right? The expansion gets longer and longer and longer and messier and messier and messier, okay? So if you want to do this expansion here, we call this a perfect cube. What happens is it takes this general form, and if it's a take b all squared, that should be cubed. So can you fix your notes up there and put a cubed in? Equals that. And these are two different identities, and if you asked me to write them out, I wouldn't have a clue. Okay, so the method I use to expand is pattern recognition, leading me to this thing called Pascal's triangle. All right, so how does it work? Well, I'm going to think of a perfect square like a plus b to the power of 0. Not a perfect square, but a power 0 expansion. That's just 1. Anything raised to the power of 0 is 1. If I've got a power 1, that's just the same as x plus b. Okay, if it's all raised to the 1, it's just 1 and 1 as the coefficients. Power 2, if I was expanding that, hopefully you know that that's going to be x squared. 2 times that is 2xb plus 1. And what we're focusing on is the coefficients that come out here. Right, with a power 3, you're just going to have to trust me on that when you expand that, you're going to get a 1, 3, 3, and 1. Now, that leads me then to know exactly what's going to happen with these coefficients. Okay, so I know how the coefficients of any expansion I'm going to do are going to come out. Now, I can generate these coefficients for any power that I want. Okay, so I want a power 5, I can get you that list of coefficients. So I'm going to pretend like that's not there. Don't cross it out on yours. I'm going to pretend like it's not there. Right? And then I'm going to rub it out in a minute or two when I tell you what the coefficients are going to be. Here's how I do it. Pascal's triangle works such that I write 1 at the top. Then I write 1 and 1 underneath. Then I write 1, and what I do is this number here is going to be 2, which is derived from the addition of the two numbers above it. 1 is derived from the addition of the two numbers above it, which is 1, and on this side, 0. This one here is going to be 1, which is derived from 1 and nothing. And we continue in this fashion here. So this number here is going to be 1 because it's derived from the addition of 1 and nothing. This number here is going to be 3, which is derived from the addition of 1 and 2. This one here, 1 and 2, 3, 1. This one here is going to be 1, 4, 6, 4, 1. And if you notice here, what I'm generating is the coefficients 1, 4, 6, 4, 1. 1, 3, 3, 1. So this would be the coefficients for a power 0, power 1, power 2, power 3, power 4. Okay? And the power 5 coefficients will be 1, 5, 10, 10, 5, 1. Okay? So I'm not going to rub that out. I'm being cocky here, but I know I'm right. So this is more formally what it looks like. That's Pascal's triangle. And so to do these expansions, this is how it's going to work. Okay, so x plus 3 all to the power of 3 is going to equal. Okay, so here's the method that you use. You write down the first coefficient, which is going to be 1, because we're on, so this is row 0 or power 0, power 1, power 2, power 3. This is the row that we're interested in. So I write down 1 as my coefficient. Then what I do is I cube the x, and whatever this thing is, I raise it to the 0. Then every time I do it, I just put a plus sign in, and then I keep going in Pascal's triangle. This is going to be a 3. Now what happens is the powers on this one here decrease by 1, the powers on this one here increase by 1 each time. This is going to be 3x squared, 3 to the 1. This has gone down by 1, this has gone up by 1. See if you can anticipate what the next one's going to be. It's going to be 3x to the 1, 3 to the 2. And the last one is going to be 1 coefficient, x to the 0, 3 to the 3. Okay, so now let's clean this up. X to the 3, so 1 times x to the 3 is x to the 3, 3 to the 0 is 1, so the first term is x to the 3. This one here is going to be 3x squared multiplied by 3, which is in fact 9x squared. This one here is going to be 3 squared is 9, 9 3s are 27, x. This one here is going to be x to the 0, which is 1. 1 multiplied by 1 is 1. 3 to the 3 is 27 plus 27. Now, if you think that's hard, it is, and it takes some getting used to. And so don't think that that hasn't taken some practice for me. There is another way of doing it. So you can go x plus 3, x plus 3, and x plus 3, and actually run an expansion. So what you do is you expand that by that, that by that, that by that, that by that, and get a result, which is going to be x squared plus 6x plus 9, then multiply by x plus 3. And that by that, 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 that by that. You can see by the amount of arrows here, I'm just like, oh my God, I'm not doing that. If the numbers are higher, it's much more clunky. And if it's a power 4, forget that, okay? So this process here, Pascal's triangle, is much, much better in my opinion. Right, so here's a tough one. Okay, so this is pretty tough for year 11 level. So we're going to note that it's a power 3. So what I would do, pretending that Pascal's triangle isn't there, I'd go, what are my coefficients going to be? So I'd be like on the side of the page, it'd be like 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. They're going to be my coefficients. So now I'm going to write down 1. Now this one here, it's going to be x to the 4, x on 4 to the 3. So I start with that being raised to the 3, and then it's going to be negative 2/3 to the 0. So this one always starts at 0, this one always starts at 3. Then I'm going to go 3, which is the next coefficient according to Pascal's triangle. And I'm going to go x on 4 to the 2, negative 2 on 3 to the 1. Then I'm going to go 3, x to the 4 to the 1, negative 2 on 3 to the 2. And the final one is going to be, a bit optimistic with the space here, 1, x to the 4 to the 0, negative 2 on 3 to the 3. All right, so sorry about the dodgy space on that. Okay, now let's clean this up. It might take a few moves to get it nice and tidy. So this is going to be 1 multiplied by, that's going to be x to the 3 over 4 times 4 is 16, that's 64, multiplied by that, which is raised to the power of 0, which is 1. Cool. This one is going to be 3 lots of x squared over 16 by negative 2/3. This one is going to be 3x on 4 multiplied by, it's negative and it's squared, so it becomes positive, 4 on 9. And the last one is going to be 1 multiplied by 1, negative 2 to the power of 3 is negative 8 over 27. Okay, so I'm just going to continue this down here. All right, so that's going to be x cubed over 64 plus, no, it's not going to be plus. We're going to have 3, so positive 3 multiplied by this negative. So this is going to be take away. So 3 times 2 is 6. So we're going to go 6x squared over 3 times 16, that's 30, 48. Okay, plus, oh my God, this is getting big, isn't it? That is going to be 12x. 9 4s are 36. Take away 8 on 27. But wait, there's still more. Okay, so what we've got to do is just simplify these fractions. X cubed over 64. Take away x squared over 8 once 8 times. This one is plus x on 3, take away 8 on 27. All right, so if you think again that's pretty tough, yeah, it is. But those of you who then want to go x on 4, go x on 4, take 2 on 3, x on 4, take away 2 on 3, x on 4, take away 2 on 3. Try that out if you really want. And I bet you, well, I shouldn't say I bet you, but I predict that you get it wrong. All right, so the homework, girls, is going to be just exercise 6A. Don't worry about these handouts. Okay, so forget them. So just the Cambridge stuff. Get through that and get in touch with me if you've got any questions.